Start this parallel session on wind engineering. Welcome all of you. We can start with the first presentation, flutter derivatives of distortionable twin box bridges deck from ERIES simulations. The speaker is Guillermo Martinez Lopez. Please.
Can you hear me? Yeah. Okay, so good afternoon, everybody. My name is Guillermo Martinez Lopez. I come from the Technical University of Munich, and I'm part of the user group of the ERIES DISTEC project, which has as an objective try a novel mitigation strategy against flutter in long-span bridges. We will be making the experiments in the University of Genoa, but the experiments have not been taking place, so I'm here to talk a little bit about the idea behind this project and what did we do until now and which work did we do to plan all the experiments. I'm sure in a session called Wind Engineering, I don't need to introduce flutter, but it's always nice to show the example of the Tacoma Narrows Bridge in 1940. It's a obvious flutter example, and since then the bridges, we advanced a lot in the study of flutter, but at the same time bridges have become longer and longer and lighter, which also means that they are more vulnerable to flutter. At the end, nowadays, with really long-span bridges, flutter is one of the main conditions to satisfy. So there's a lot of effort in finding solutions that we can use to mitigate this phenomena. Here I show some examples. Apart from other things, there were some authors that tried to use mobile flaps at both sides of the deck and then kind of deform, to amplify the effectiveness of this geometrical modification stiffness. These are not all of the examples, just some of them. However, these mobile things, as far as I know, they were never applied into real bridges, and nowadays the idea of long-span bridges is to use, the tendency is to use more and more twin box decks because they are more stable against flutter. So I mean, they are a really nice solution. We have here the example of the Chanakale Bridge, which recently broke the record for the longest span bridge in the world. And as it is common now, you use two different boxes, one for each direction of traffic, and this has given more results and more stability against wind effects. The idea behind this is usually you have some connection between the two boxes, and usually you try both boxes to be completely tight, so a completely rigid connection, so you try the whole cross-section to act as a whole, as a single rigid body. However, we are exploring the same line that previous authors did with these mobile structures. We are exploring the possibility to change this rigid connection for something more flexible, so you are kind of allowing the distortion between two boxes, and then basically it's like if you have two flaps, but you have maximum performance of this solution because each of the boxes is a flap itself. It's a really big thing. Of course, there's no easy way to know if this is working or not because with the extra degree of freedom come new flutter derivatives, and nobody ever did research on this. But what we could do, and we did some years ago, is some early preliminary studies using the analytical flutter derivatives of the flat plate. And when we used that, we considered each of the boxes flat plate, then we found that the critical wind speed can increase up to 40 to 50%, which it was really good. So that's encouraging. We want to pursue this idea, but of course this is not worth it if we don't come with other CFD simulations or experimental testing to complement this and find the flutter derivatives of actual cross-sections. So there is where ERIES comes into place. My chair, the chair of structural analysis, has a long history of dealing with numerical problems, a lot of CFD simulations. We also have high-performance computing resources in the SuperMOOC supercomputer managed by LRZ. But of course, this case requires a little bit more. No? This requires also the combination of CFD with experimental methods because we have nothing to validate our simulations with, so we really need these experimental results. And that's why ERIES comes into play. However, this is not as simple as just finding the flatter derivatives of a rigid bridge deck. There are a lot of uncertainties and questions, open questions that we need to ask. The first one is we are completely blind. We don't know which cross-sections will work or not. It might be that some geometries work and are really effective, and some other geometries, they are not working together with this mitigation strategy. So we need to test different types of cross-section and see how they perform. The second one is, of course, we will have extra factors to take into account. For example, it is really sensible, the topic of the influence, the dynamic influence of the first box onto the second box, or there are other things that come into play. For example, the horizontal distance between the shear center of one of the boxes and the center of mass. There's an horizontal shift, and in this case, since we are moving the cross-sections, the boxes individually, this might have an effect. And finally, how can we basically find 18 derivatives associated with 3 degrees of freedom in the wind tunnel? It's not an easy task. Classical approach is to do free vibration tests. The idea will be just to have the typical model, but instead of one bar going through the shear center of the cross-section, you have 2, one for each of the boxes. The problem is you need to have a system of springs connecting both boxes. It's not ideal. This model is really delicate. So we decided to go with the other approach, which is using force motion tests. Of course, we could try to excite with 2 force motion devices both boxes, so we can excite the global degrees of freedom, but it makes no sense to have 2 force motion rigs. It's of no use to the testing facility, so instead we decided to go only with one and try to excite one of the boxes at a time. Considering all these limitations and open questions, we decided a project plan, not only with the wind tunnel experiments, but also with a complementary ERIES campaign that we will carry out in parallel. The problem is that, of course, both things are really expensive, computational resources and, of course, wind tunnel time. So we need to know a little bit more before we go and test some of the cross-sections. In this sense, we decided a kind of a lower fidelity simulation campaign to kind of come up with more information, test a lot of different shapes, do some checks if we can really find the derivatives indirectly by exciting each of the boxes individually, and so on. When I'm talking about if we can excite each of the boxes individually, I talk about these selections of degrees of freedom. Of course, now we have an extra degree of freedom. The standard way will be to say, okay, we have the deck center degrees of freedom where we have the typical bending, typical torsion, and then we will have the distortion here. And the distortion comes with another set of derivatives. So we have extra derivatives associated with the distortion and the distortional moment. I will try to summarize all this. You all probably know these formulas, but I will put them in matrix form. So we have here the forces, the resulting forces, and here we have the displacements that we are imposing. We will have something similar here with the velocities, but for the sake of simplicity, I only leave that. The whole idea is that when you excite with force motion one of the degrees of freedom, and then you try to fit the curve of the lift, in this case, you will fill one of these places of the matrix. And then you can do basically that, scrolling through the different forces and degrees of freedom until you kind of fill all this matrix. The problem is that if we are exciting individually each of the boxes, we are not filling this matrix here. We are filling a different one, which is associated with this box center degrees of freedom. So we will need to go from one reference system to the other, and that we will do with a transformation matrix. No? So at the end, it's really easy to, thanks to the linearity of all these equations, we can just apply this transformation matrix, and basically we will find the derivatives with this 4x4 matrix and then convert it to the 3x3 matrix, which is what is interesting to us. One of the first tests that we did is try to find the derivatives with the deck center doves and then with the box center doves and make the conversion and see what's the result. And the result was in general satisfactory. So we have really good agreement in most of the derivatives. Of course, we have 18 derivatives right now. We have some discrepancies in the A4, D4, and H4, but those are famous to be really difficult to capture. vector. And then we have also some discrepancies in H7 and H2. But if we look at the duals, we can see that there's a big change in order of magnitude. So it's not a big relative. So it's a big relative error, but not a big absolute error here. The next step, okay, is we can use this approach in the wind tunnel to obtain the derivatives, but now that we tried and we checked the linearity of all these equations, we can go one step further and use the multi-frequency approach. Usually you excite only one frequency and then you sample one point of the derivative. No? The idea is, instead of using one simulation for each of these sample points of the derivative, what happens if we superimpose several displacements to the bridge deck? Then we will have a superimposition of all these forces, and one by one we can extract the derivatives associated with this experiment. So at the end we are saving a lot of time. So at the end we are in a situation, these are the results of this approach, where we are comparing single frequency in red, so that's the classical approach, with multi-frequency in both shades of blue. One is imposing the same frequency to all these frequencies to the same degree of freedom. The other one is imposing different frequencies to different degrees of freedom. And again, we see general agreement in the flatter derivatives. So once we have that, we are in a position to really start testing a lot of shapes, because we have a really efficient workflow to find the flatter derivatives of some bridge decks. So we basically started to see which geometries could be interesting to see. No? We decided to go with 3 base variations. Here you can see them, and then we chose 2 variations of some of these parameters. For example, the lead word angle, or the inner cell angle, or also the distance between the boxes. In total, that means 18 different geometries, 18 different sets of flatter derivatives, and in total that means 270 simulations. And of course, if you have 270 simulations, the result is a lot of points and a lot of lines. And I think you will all agree that it makes no sense to talk about derivatives anymore. So these are different shapes. So the comparison between derivatives is not meaningful. They, of course, will be difficult. And we need to go one step further and start talking about the critical wind speed, not the derivatives itself. So we want to complete this extra step. We are here, and we want to talk about the critical wind speed of each of the shapes, so we can compare which shapes perform well with this mitigation strategy. The problem is you need extra inputs from here. You need structural parameters, and you have also a lot of uncertainties in this process. So we need to go back to the thinking mode again and start thinking about what can we do to make a robust analysis, because it's not as easy as taking the derivatives and saying, hey, this perform better. They depend on a lot of things. The first one will be, which structural parameters do we use? Do we use the ones from the Chanakale bridge and that's it? Should we use several of them? Should we use variations? The next question is, probably there are some parameters that are really, really determinant to evaluate the effectiveness of this mitigation strategy. For example, we saw in preliminary results that the results are really sensible to this position of the shear center with respect to the center of mass, which makes a lot of sense. That's something new, and that's something that needs to be studied. Of course, we used a lower fidelity model to abstract all these derivatives, so it would be nice to do some kind of sensitivity analysis to be sure that our results are robust and that small variations in this fitting of the curve won't affect qualitatively, at least, the results. And even the smallest things, so for example, the arbitrary shape that we use to make these derivatives continuous, we can change and see if they have an impact. What I want to say with all these slides is to say there's a lot of work here. Of course, we don't need computational resources to do all this analysis. We don't need wind tunnel time to do this analysis, but we do need a lot of human time to do that. So actually, the plan that I showed before, I did here a small modification. We were saying that we had the Urans campaign in winter. That's already done. And we were planning to start probably with the ERIES campaign in summer, hopefully. And the gap in between that we didn't mention before, spring, which is what we are doing now, will be to do this evaluation of results. And that's exactly what we are doing now. So that's it from my side. I have only left to say thank you everybody for listening, and thank you, of course, for the ERIES program to help come to life a project like this one. Thank you.
Thank you, Guglielmo. And questions, comments? Yes.
Very nice work.
Microphone.
Very nice work, again.
Thank you.
So just these results, was it all urans?
Yeah, all this, what I showed today is urans. The idea is to, once we do all this analysis, we select the shapes that perform the best, and these shapes will be tested in the wind tunnel, and in parallel, we will test with a higher fidelity model with ERIES, like long simulations in the supercomputer.
I'm just curious if there is a possibility to how to model the springs connecting the decks and their stiffness in urans, so and later in ERIES. So
yeah, so we used forced motion approach. That means so it's not free vibration. That means that I'm imposing to each of these displacements or each of these degrees of freedom, I'm imposing a sinusoidal motion. So in my simulation, I'm modifying the geometry, I'm modifying the mesh, but it's not an FSI simulation. I'm not solving the structure at all. So I'm just imposing a prescribed motion. The springs don't matter for the CFD. Just have the sinusoidal motion, I extract the derivatives, and the stiffness of the springs come later in this point. When you do the solution of the flattest equations, of course, there you need to consider the stiffness of the springs.
And then just a quick one. Does it make sense to do all the derivatives, or just take like the main one for the heave and the other one for the torsion, perhaps combined? Flutter, so double degree,
okay,
instead of doing all of them?
Okay, I suppose not all of them are equally important. That's something that happens also with 2 degrees of freedom flutter, a classical one. There are some analyses that we did, sensitivity analysis, that kind of show which derivatives are more important. For example, we showed that derivatives 4 usually are not that critical for the critical wind speed, these kind of things. However, we don't know that yet. So at this moment, we really need to obtain all the derivatives, and this kind of analysis and questions is what we are trying to solve now, to say maybe in the future we don't need to extract these derivatives. I will say also that some of them, at the end, you need 3 simulations, one for this and this column, one for this and this column, and one for this and this column. So if you want to extract, for example, the H2 derivative, it takes only one more core fitting, no simulation at all. So like seconds in the computer to obtain the H2 and D2 and H3, A3, D3, because they come in a pack as well. They come all from the same simulation.
Okay. Thank you very much.
Thank you.
Thank you again, Guglielmo.
Thank you.
And we go on with the second presentation. The presentation is about evaluation of force coefficients on a lattice structure by experimental wind tunnel tests, and the speaker is Gert Lambert. Please.
Okay, thank you very much, Maria Pia, for the introduction. So I'm presenting here this work on behalf of a group of authors, as you can see on the title slide. So authors from KU Leuven and CUHAI, located in La Habana in Cuba, which were part of the user group of this project, and then colleagues from the University of Genova, which is where the tests were performed. So as clarified by the titles, these tests have been performed to identify the aerodynamic coefficients, the force coefficients on a lattice structure. So just to motivate this work, which has been performed within the frame of the PhD of Bruno Clavello, the main and the first author of the corresponding paper, to motivate this work, you can see here a number of photos, which are all from cases where antenna masts have failed in the last 15 years. These antenna masts are all in Cuba and have failed in strong wind conditions. And it's clear that such failures do not only present important economic losses, but are also problematic because they're important to ensure communication in catastrophic or disaster events. So within the PhD of Bruno Clavello, we try to develop a better understanding in the actual wind loads on structures. And we do that by developing model-based system inversion techniques for the estimation of the loads. So just to clarify what we mean by the model-based system inversion, in a conventional design process, you would take the design wind loads and use these with the model of the structure to predict the response. Here we take the inverse path where we use measured response coming from a set of accelerometers and strain gauges, and with the model of the structure we try to reconstruct the wind loads which drove the response that was recorded. So that is the subject of the PhD. We have an actual case study of an antenna mast in Cuba, which is located in Santa Cruz, and you can see that it's a guide mast. So the lattice tower here is supported by a number of guys. And then two types of experiments have been performed. First, we've done an extensive operational model analysis to identify the natural frequencies of this structure, and then we've used those model characteristics to update the finite element model of the structure, because in system inversion it's very important to have an accurate model of the structure, because otherwise your loads that you identify will also compensate for modeling errors. And then we have a longer term monitoring campaign in which accelerations and strains have been recorded on a number of months, together with wind flow data captured by anemometer measurements. So the aim is to use these data to estimate the loads acting on the structure, mainly modal loads, and then we'd like to use the wind flow data to sort of estimate the loads and use these as a validation of what we identify based on the acceleration and the strains. And the ERIES project has actually made it possible for us to estimate or to identify the aerodynamic coefficients that we can use together with the measured wind velocities to estimate these loads. So what I will report next are the wind tunnel tests which have been performed to identify, to estimate these coefficients. So the main purpose of those tests was to estimate those aerodynamic coefficients, but also to determine the contribution of the different ancillaries, the different antennas which were present on the antenna mast, to also have a better understanding of how these contribute to the drag and lift forces of the tower. Also because in many cases such antennas were not originally considered in the design or have been included at a later stage of the operation and were not always taken into account in the actual design of the structure. So here you can see a drawing of the section of the lattice tower, and you can see the different types of configurations, let's say. So we have the bare structure, we have the one with the linear ancillaries, as we call it. So these consist of stairs and then cables, feeder and data cables. And then you can see 3 different types of antennas with which the actual antenna mast has been equipped. So in the test, we also want to identify the influence, the contribution of these antennas. So we've done a test with a sectional model of that lattice tower. You can see here the level of detail which is in the sectional model, where you can see that all the individual members are present in the model. And then you can also see how the discrete ancillaries were represented, also with a high level of detail. And these could be easily added to the actual sectional model, in particular for the discrete ancillaries, so that we could easily remove and include them throughout the various tests. So the wind tunnel has already been introduced in some of the previous presentations, so I'll limit myself here to indicating the section of the wind tunnel where this test was performed. So previously the tests on the building were performed here at the rotating table. Here we are closer to the contraction cone, and the test section was actually fitted in between 2 force balances that allowed us to measure drag, lift, and moments. So here more close up with the section of the wind tunnel over here, the force balances, and these force balances were also connected to a rotating support so that we could also repeat the test, repeat the identification of the coefficients for different angles of attack. So the tests were performed with a maximum step of 10 degrees in this range. I should also indicate here that the structure, the section is not fully symmetric, also the bare structure, because of the orientation of the steel angles, which are the main longitudinal elements of the lattice tower. So here you can see a photo of the sectional model fitted in the wind tunnel. The tests have been performed a little more than 1 year ago. We also had some equipment for measuring upstream and downstream wind velocities. We had tests performed in smooth flow conditions as well as turbulent, at least for the bare configuration. Also the turbulent conditions were considered. And of course, a number of things were checked to ensure that the results were reliable. So what you can see here are the mean forces and moments, which have been measured by the force balances. So you can see drag, lift, and moment. The vertical scales are slightly different, so it's not surprising that the direct forces are considerably larger than the lift forces. You can also see the lines which represent the different configurations of the sectional model. So the bare model, the one with the linear ancillaries, and then we have 3 different sets where, in addition to the linear ancillaries, we had a number of we had 1 additional discrete ancillary. So you can see quite a big step going from the bare structure to the one with the linear ancillaries, and then some smaller differences with the different antennas mounted on the sectional model. So as said, the bare structure was also not perfectly symmetric, explaining why there is a kind of quasi-periodic but not perfectly periodic pattern with angles of 120, 240, 360 degrees. So from these forces, we've also estimated the aerodynamic coefficients, so with the expressions presented on the slide, with also a reference area which was considered the one for an angle of attack of 0 degrees, so one of the orientations of the sectional model, which was then maintained for all the other angles to compute these coefficients. So these are the results. Again, drag, lift, and moment. So again, you can see that the drag coefficient is substantially larger than the lift coefficient. And you can also see some areas where the drag coefficient is in particular quite different for the bare configuration and the one with the ancillaries. So this is quite clear, around 90 and around 270 degrees. And so you can see the projected areas for at least the angle of 270 degrees. And this is a table summarizing the results and also highlighting let's say, the increase in these coefficients, and here the increase actually in the drag resistance. So by multiplying the coefficients with the projected area, and so you can see a big jump going from the bare structure to the one with the linear ancillaries, with an increase of up to 40%, and then some additional increase going to each of the antennas, so which means that they do contribute significantly to the drag resistance of the section. So these results are now available. We're currently incorporating in the research of Bruno in the study where we do this inverse estimation of the wind loads. And so we feel that these results may not only serve the research of Bruno, but could also be interesting for a number of other problems. And for this reason, the results are also made available through Zenodo. And actually the data paper, which is where these results are presented, has just been accepted last week for publication. So the data paper and the repository will soon be fully open for people who are interested in using these results. So with this, I'd like to conclude and also thank the EU for the funding, and in particular the ERIES project, which made it possible for us to do these wind tunnel tests. I'd also like to acknowledge the support for the scholarship of Bruno Clavello, and also very importantly the assistance from the entire team in Genova in helping and supporting us in these wind tunnel tests. So, thank you.
Thank you. We have time for one question, if okay.
Thank you for the presentation. Maybe I missed it at the beginning. Oh, sorry. Thank you for presentation. Maybe I missed it at the beginning. I want to ask you about the Reynolds number similarity here in wind tunnel. There are tubular parts of this guide mast, aren't they? Or
yeah, we actually checked, I think for Reynolds number around 10 to the power 7, 10 to the power 8, if I remember correctly, to what extent these results were independent of the Reynolds number. So for those values at least, we found that was the case.
thank you.
Okay, quick.
Quick one. Thank you very much. So you put the model horizontal and like the lattice tower model, and then in the full scale, if I'm not wrong, it was like 80 meters high. So basically there could be like effects due to not simulating the standard ABL profile or thunderstorms or
yeah, so we indeed chose to do a test on a section rather than a scaled down version of the full model.
Yeah.
Because that is, of course, far more complicated.
Yeah.
Because then you also need to reproduce the full wind velocity profile.
Yeah.
I think the aim was to have the aerodynamic coefficients and to use them in a similar way as we do when designing structures against wind loads.
Just a slice of a tower.
Yeah.
Okay.
So,
Okay. Thank you.
Fair question. Yeah.
So thank you again, Gert.
Okay. Thank you.
Next presentation is wind tunnel testing of flexible advanced aeroelastic models of bridge cables, and the speaker is Stanislav Popslis.
You can say whatever.
Sorry, it's too difficult for me.
Yes. Just how to put the presentation on. Presentation slideshow. Okay. From beginning. Okay. Thank you for introduction of mine. I would like to introduce the project which was called ERIES Flamberg, and it was done by cooperation of 3 institutes, ETAM, which is our institute, then Technical University Opole and CSTB Nantes in France. Involved was about 9 researchers and 7 technicians, and I'm speaking on behalf of the team which is here. This is my former PhD student who did a lot of work on preparation of the experiments and analysis, and on behalf of Armando Caruso and Olivier Flamand from CSTB. As Olivier said, I will not tell everything today. I will tell just half of it because 2 reasons. One, I want to make additional presentation in Trondheim. And the second reason is that not all of the data was evaluated, so I will show the data about the frequencies and Strohal numbers evaluation of this. Why we chosen this name Flamberg? Flamberg is an ancient sword which has a wavy shape, so we were thinking that our testing sample will resemble a little bit of this sword. So the project, as was said, was dealt with a study of wind-induced vibration of bridge cables or cables in general, and we were focusing on make this cable elastic so that we can reach higher frequencies of vibration. This procedure, which I will show, can present any shape of this, like a spiral strands or cables covered with glaze ice, etc. And the important is that we can finely tune the frequencies of this cable, of this specimen, so that we can also simulate naturally three-dimensional behavior of this specimen. So it was also focused on the improvement of testing facilities and developing experimental methodology for laboratory simulation. So advanced aerostic models were used to study VIV vibration of, as I said, of the higher natural modes. We also studied the influence of the accretion on the cable, or, as I said, can be any modification of surface roughness. And the 3D data will be soon available also for any other researcher among us. So it is what the ERIES project or ERIES idea is serving for. So what's shortly about the test specimen? We decided to make a cable. This is a little bit exaggerated. This is not like this. This sac is not that big, but it's composed from the rigid parts made by additional manufacturing and also flexible parts from TPU sections. Inside of this cable is a steel cable, which is there because we can change the frequency of this. How it looks like inside, so we have a stiff part and we have a flexible parts together. It's like a snake a little bit, and inside there is a flexible, there is a steel core cable used for the tensioning of the specimen, and inside there are also cables which are stabilizing the rotation of the cable. I will not go into the details. This is just schematically here described. You can read it. We were testing two types of the cables for this measurement. It was done in November last year, and we were testing the smooth cable and cable with the ice accretion, which we prepared before and printed in our wind tunnel in Prague. We were testing three types of accretion, or let's say angles of the accretion. Inside of this cable, which was 4 meters, more than 4 meters long, were 4 accelerometers with this scheme, so that we could also identify not only the vibration in drag and lift, but also in the rotation. And they were these small 2-gram accelerometers Brelkier. In total, there was 8 of them. This is already a look at the experimental setup in the wind tunnel in CSTB. And this is the scheme of the frame which was holding the cable. It was pretty stiff one, because here on this side and this side we could adjust the pretension of this. The total mass of this was 1 ton and 250 kilograms, not the cable of course, but all together. And the blockage was about 7%. Here is the schematic how the tension was provided. So this was on one side, this was a mechanical threaded tensioner. On one side, this one was used for adjusting the frequency, by just moving the distance of this plate, steel plate, here. It looks like here. And on this side was used for the pretension of this auxiliary 4 smaller cables to hold the cable in the non-rotational position. Of course, on both sides, 2 flat screens were added, one for the yaw angle 0 and one for the yaw angle 15. So we did actually 2 tests on different yaw angles. Here is the plan view, how it was put in the wind tunnel. So you can see that the length was about 4.5 meters. There was a space 800 millimeters, and here are the plates, the side plates, and the flow was measured by Cobra. One was here in the windward side, about 3.5 meters from the specimen, and 2 Cobras were measured, put here where the accelerometers on the plane where the accelerometers were put. The distance was about 5D. Also, we observed the whole vibration. We recorded it with the cameras. One camera was above the specimen. One camera was here in front of the specimen. And now to some result, which is, I think, the most important or interesting things. Here we can see the development of the straw hull of the frequencies through the velocity range. We were going up with the velocity and down. You can see these bullets and also the asterisk two ways of the adjusting velocity. The straw hull number here in this case was 0.196, and it was smooth cable for the yaw angle 0. You can see that we really identify 4 eigen frequencies. This was the first mode, and you can see also that with a higher velocity, you don't have this plateau here, like in the first and second mode, because of the drag was pulling the cable, so it changed a little bit frequency of. So here is the second mode. You can see also here that it really vibrated in the second mode. And going up, third mode, straw hull number still the same, and and so on. Now I will show the case of the smooth cable with higher pretension level. So we were at the first part was about 5 hertz of the frequency. Here the tuning of the string was 10 hertz. So we can see first mode here and the second mode. We didn't went up because there was too dangerous for the accelerometers. Here it is quite interesting. We changed the yaw angle from 0 to 15 degrees, and what we can see here, maybe we can discuss it. I welcome any of your comment. These are identified vibration frequencies by accelerometers. So really, we have 5, 10, 15, 20 hertz. Here, however, for the straw hull numbers, we can see first frequency, second frequency, but going with the velocity higher than 6, we can see that there is a big dispersion of the points, even going up and high. And my theory or my hypothesis, my explanation is because this yaw angle so that the roughness of the cable or even small roughness can change this coherency of the vortices, and it's so distorted. So there is not visible Strohal number effect or this lock-in effect. With ICE cable model, angle of attack 90 degrees, so the ICE is down, and low pretension, only 5 heads. We went into 10 heads, and your angle 0. We can also see the development of frequencies with velocities, up and down. And what can we see here? With a yaw angle here, 15 degrees yaw angle, we also have this structure of this lock-in effects at each frequency. And I mean not each, because the fourth is not visible here, but first, second, and the third is visible. And because it's already, the turbulence here causes that we don't have this dispersion of the frequencies there. Maybe you would ask, how was with the damping? So the damping of the cable was very low for the case of the 90-degree ice and the smooth cylinder. It was about 0.02 critical ratio. However, when we put the ice cables in this direction, it causes rotation of this cable, and we measured the damping, which was order higher than in the smooth case. So, before the preparation or during the preparation, we took the comments from the evaluation panel. So we eliminated some problems with the 3D printing and with the damping, with the cable tensioning, putting inside the cables and so on. And I think these experiments were quite successful. We are working on the analysis of the amplitudes and the accelerations, which as I said, probably will, or a colleague of mine will show in next conference in Norway. So thank you very much for your attention, and this is our nice team, all young, nice people you can see here. Thank you very much.
Thank you very much. I think we don't have time for questions because we're a little bit late, so we move.
I was more than 15?
15, exactly.
I welcome your questions and comments about it.
Yes, in the coffee break. So we can move to the next presentation, which is wet snow accretion on overhead conductors, experimental study in a climatic wind tunnel, and the speaker is Francesca Lupi. Sorry.
Yes, good afternoon, everybody. In this presentation, we'll be talking about wind and snow. So wet snow accretion on overhead conductors, so transmission lines. My name is Francesca Lupi. I'm from Niemann Engineers. It is a wind engineering consulting company in Germany. We are a spin-off of the Ruhr University Bochum, and in this constellation we applied for this ERIES project. There you see the list of my co-authors and people of the user group. We have an industrial PhD student from Ruhr University Bochum and the research, infrastructure structure was CSTB in France. So we are talking about transmission lines, and the final goal of the investigation is to be able to have realistic estimation of ice loads in view of structural reliability analysis of transmission lines. The specific objective of the ERIES project was to better understand, validate, and extend the existing ice load models in laboratory conditions. Why are we doing that? There have been several structural failures also in recent years due to wind and snow. The picture that you see there is a catastrophic event which happened in Germany in 2006. It caused a lot of damage. The phenomenon was wet snow accretion, what we are talking about. So this arose the questions among network operators, what is the actual risk that we have? And this question is important not only for the new design transmission lines, but also for the existing transmission lines. And the best approach to estimate the actual risk is a probabilistic approach based on an extreme value analysis. But for that, you need to simulate time histories of ice loads based on meteorological data. And if you're able to do that, then you can calculate annual maxima and do your analysis. But the link between meteorological data and time histories of ice load is the missing link that we have tried to investigate with this project. There is an approach in the literature, a very well-known and established approach to calculate ice loads. This approach was developed by Makonnen. It is able to calculate the mass of accreted ice on a conductor per unit time, so in 1 second or in 1 hour. You have to imagine a flux of snow particles in the air. So you need to know what is the mass concentration of the snow in the air. And then you need to know the impinging surface, so basically the diameter of your conductor, and the velocity. Because if the wind velocity is higher, you will have more particles in the unit time. But this is not all, because we have the so-called efficiencies. So one should know what is the fraction of the incoming particles which really hit the conductor and are not displaced at the side by the wind. If all these particles that hit the conductor stick on the conductor or are bounced off, and if all the particles that hit the conductor stick on the conductor really build ice, or maybe there are water runoff. We made experiments in CSTB supported by ERIES. It was 1 week of experiment last October. And here you see the entrance of the wind tunnel, and in order to generate snow, we had a snow gun. The snow gun was placed at the entrance and in a reverse position with respect to the flow. Here there is a video where you can see how the snow gun were placed in the right position during the test. In the reverse position with respect to the wind. The wind was flying with a constant wind velocity. So now we see that the snow gun is adjusted in the right position. And on the other side of the wind tunnel, there is the conductor, our model. And the important thing is that the temperature of the wind tunnel is cooled. So we are at between -2 and -10 degrees. And the snow gun injects water particles in the air. These water particles find this cool ambient temperature in the wind tunnel, and they progressively freeze. So they are partially freeze when they impact the conductor. And this partially frozen is the important parameter which decides the amount of accreted ice on the conductor. This is our model. It is a one-to-one specimen of a real transmission line, 2 meters long, and the model was suspended and pre-stressed. Pre-stressed because we had to eliminate the sag due to the self-weight and also manufacturing, and suspended because we also wanted to replicate in the wind tunnel typical conditions that we have in full scale. If you imagine imagine a 400-meter, 300, 400-meter long transmission line. In the middle, the torsional stiffness is very low. So because of the weight of the accredited ice, the conductor is able to rotate. And in the experiments, we wanted to reproduce this condition, very high torsional, very small torsional stiffness, and on the other hand, also high torsional stiffness, so non-rotating conductor. We had force sensors at the two ends of the conductor to measure the horizontal loads and the vertical loads. And this is the testing program. The main parameter that we changed during the experiments was the temperature in the wind tunnel. The temperature allowed us to test the different qualities of snow, drier, wet snow, very wet snow, and this was the first objective of the experiment, to investigate the effect of the snow quality on the mass of accredited ice. The second purpose of the experiment was to investigate the effect of the conductor rotation. And the third one was the effect of the wind direction. We didn't go too much into details of that, but it is important for the probabilistic approach because the wind is not always blowing in the most unfavorable wind direction. So these are just some highlights. We see that in case the temperature is very small, very low, the snow is dry, and dry snow produces small accretion because most of the particles are just bounced off the conductor. They are ice particles. If the snow is wet, and this happens because the temperature is a little bit higher, then we had very significant masses of ice in the order of some kilos in 1 hour. This is a typical form that we had when the conductor was fixed, so not rotating, and we see this vein at the windward side. And if the snow becomes even more wet, we are going into the direction of freezing rain. So basically, it's not snow, it's almost rain when it is impacting the conductor. In this case, we see water runoff, so the formation of these ice cycles. In order to capture the experiment, not only the force measurements were enough, we also needed to somehow capture the shape of the ice. And for that, we used the 3D scanning, which was able to reproduce the three-dimensional geometry of the ice. And we used this grid. The scanning was available as the STB. And with this grid, we could, it was possible to create a reference point for the scanning of ice. So we could reproduce also the shape of the ice, not only the weight. So some results. Here we see the accumulated mass, the accreted mass per meter in 1 hour of test. And on this axis, we see what we call the liquid-water ratio. It tells you how wet is the snow, so how sticky is the snow. It varies between 0 and 1 in non-dimensional terms. In 0, you have ice. In 1, you basically have rain. In between, you have snow, which is a mixture of liquid and solid phases. If we have dry snow, we have very small accretion. If the snow is wet, the accretion increases almost in a linear trend, I would say, very rapidly, and then we see a change of slope of the slope if the snow is becoming very wet. This is because of freezing rain and the formation of ice cycles, so the water runoff effects which are responsible for this change of slope. In case of a rotating conductor, we see here a typical time history, typical test. We had, in this case, 5 15-minute phases when the wind was blowing in the wind tunnel, and then we had some phases in between without wind. We always had this in every experiment because without wind, we could measure the vertical force which corresponded only to the weight of the snow, of the ice. And in this case, we see that the shape is completely different. It tends to become a rounded shape because the accretion is developing at the windward side, and since the torsional stiffness of the conductor is very low, the conductor progressively rotates, and we saw that this rotation is almost in a linear manner. So the conclusions, we investigated snow of different qualities, and this was possible adjusting the temperature of the wind tunnel, and we tested the non-rotating conductor and the rotating conductor. And what are the next steps? We would like to go as next step from wind tunnel to full scale. First of all, there is a time scale factor, because in the wind tunnel we were able to test in 1 hour what we could obtain in full scale in many hours, maybe days. So we are accelerating the process, and this is just because we inject in the air a concentration of particles which is higher with respect to full scale. This scaling should be linear, according to literature. And the second step is to find a relationship between the meteorological conditions that we measure in full scale at meteorological station and the snow quality. In the wind tunnel, we have seen the relationship between the snow quality and accreted mass of ice, and now we need this second step to go from meteorological data to accreted mass of ice. So thank you very much for your kind attention.
Thank you, Francesca. So we have time for questions. Yes, please.
Thank you for presentation. You mentioned the liquid-water ratio, which is, of course, important parameter, the key parameter. But also there is important, I didn't see what was the humidity in the air. Because if you have a high humidity, you have a big nucleation around these particles, so it may increase the amount of snow, whatever it is, sitting on this cable. Did you measure the humidity in the tunnel?
No, we didn't measure the humidity. We measured the air temperature, and we measured the collected mass of ice through a known cross-section, which gave us information about the mass concentration of the snow in the approaching flow.
Yeah.
And the density of the snow. This is what we measured.
And the distance from this cable from the gun, did you calculate it before?
Yes, not me. It was a standard configuration at CSTB. The distance is 10 meters. It's a standard distance, and the snow gun is calibrated so that, considering the temperature of the wind tunnel and this distance, the particles are partially frozen when they reach the model.
Mm-hmm. Thank you.
Okay. Okay. Yes, thank you.
Okay, another question?
Quick one again. So thank you very much, Francesca. So I'm just curious, you showed like in the table like various types of ice for different temperatures, like in the steps of 1 degree. And then as these big wind tunnels run, the air is heated over time. So is it possible to keep the temperature constant? So just to have always the same type of ice in the wind tunnel?
Yes, the temperature was indeed kept constant. What I would like to add is that the temperature that we see here is not directly comparable to the temperature that one would have in full scale. This is adjusted because of this distance of 10 meters for the purpose of the experiment, to achieve a snow of some quality, but it's not the absolute temperature that one should directly compare in full scale. But yes, it was constant, it was kept constant.
Okay, thank you.
Okay, thank you again, Francesca. And we move to the last presentation of this section. The title is Wind Tunnel Tests on a High Rotational Urban Savonius Turbine, and the speaker is Luisa Pagnini.
Sì, sì. Connotazione. Cosa ho dimenticato gli occhiali? Ci vedo. Sorry, I forgot my glasses.
Do you want to mine?
Sì,
No.
ok.
This is here,
Ok, e il mouse?
and the mouse you can go like this,
Sì.
to front.
Ok,
and this
e
is
scusa, ok, thank you.
here in the middle.
Ok, sorry. Good afternoon. The High Rotational Urban Savonius Turbine Project is led by the team, the research team of the Gdansk University, and wind tunnel tests have been carried out at the Giovanni Solari of wind tunnel of the Genova University. The TRUST project investigates specifically prototyped Savonius rotor that had been designed without any braking systems. So the goal of this project is mainly to investigate the behavior under high rotational velocity of the Savonius model, and also investigating its behavior under turbulent conditions, and to measure the acoustic emissions. The Savonius model, the Savonius rotor, is equipped with a three-phase permanent magnet generator and a torque meter, a Hall sensor to measure the rotational velocity, and a resistive loading system that is used to control the rotational velocity of the turbine. Other measuring devices are a pitot tube at the inlet of the wind tunnel. Then we have one upstream hot wires with respect to the turbine, and one downstream hot wires. We have 4 microphones in the downstream position, positioned at different distances from the rotor. And then there is a grid that is used to create turbulence in the wind tunnel. The wind tunnel setup was quite delicate, as we had to accurately check that all components were perfectly aligned without any frictions. And also measurements were not, all measurements were not straightforward. For instance, to estimate the rotational velocity from Hall sensor, we derived this information from the power spectrum of the Hall sensor outcomes by picking the highest, the frequency corresponding to the highest peak of the spectrum. And also hot wire measurements were quite delicate. In fact, while in the turbulent measurements, for instance, in the downstream position or in the turbulence, in presence of turbulence, well, in a smooth condition, measurements were very delicate because our wind tunnel has a very low turbulence intensity. So it was very challenging to have good measurements. Tests were carried out in 3 different times. First stage in July 2023 was carried out to have the setup calibration, test of all measurement systems, and also preliminary measurements just in smooth flow. Then the second stage carried out the main measurements, both that were performed both both in smooth flow and using a thin grid, creating a turbulence intensity of about 4%, and a thick grid, creating a turbulence intensity of about 8%. And all measurements in the different conditions were carried out with wind tunnel wind speed ranging from about 4 meters per second to more than 20 meters per second. Finally, in the stage 3, all measurements were repeated, but with the main goal of achieving acoustic emissions by the use of the 4 microphones. The methodology used, the turbine was loaded. Usually we started from a high load, so the turbine was rotating slowly, and then it was brought into a stationary condition. In this case, 1 minute of record of all the quantities involved was recorded. Then the load was decreased, so the turbine was brought rotating a bit faster, and another record was acquired, and so on. For instance, this diagram just shows some results in a smooth flow in terms of average values of the rotational velocity of the turbine and the produced power. So at each fixed wind tunnel wind speed, we have the complete power curves on varying the rotational velocity. And this is done for the power and for the torque measured during the experiment. Here, different symbols indicate tests that were performed in different times. Therefore, we achieved a very good alignment that indicates a good repeatability of the test. This slide shows some measurements obtained by the hot wires, where here we have the measurement upstream, the red line, and the downstream of the turbine in an intermediate position of the power curve. Here we recognize the rotational frequency of the rotor, 1p, that it exactly matches the value obtained by the Hall sensors, and also the 2p multiple. We also recognize the Kolmogorov cascade in the downstream hot wires. And this diagram in the middle corresponds to the maximum power production. Well, here we do not recognize anymore the frequency 1p. That arises again once that we proceed in another intermediate position of the power curves. Here, this diagram resumes the power curves in smooth flow conditions. And this slide shows together some sketch, some synthesis of the results, considering also the turbulence intensity of 4% and 8%. So you can see in terms of maximum produced power that, well, the blue symbols refer to the turbulence intensity 8%, and this diagram shows that, as expected, the power production decreases with the turbulence. And the efficiency can also be investigated in terms of dimensionless coefficients, the power coefficient, the thrust coefficients, and here you see the diagrams versus the tip speed ratio at smooth flow and turbulent flow. So, as expected, the efficiency seems to reduce with decreasing wind velocity and seems to reduce in turbulent conditions, both for the pressure coefficient and for the thrust coefficients. We then carried out a very deep investigation to check and validate results, also using numerical simulations, URANS, numerical simulations, and also comparing results with the very classical findings by Blackwell in 1977 on similar Savonius. And here you can see that we found a very good alignment between results. Even, you know, the red symbols are the present results. Sorry, the red symbol, the black symbol are the present results. And here we found a sort of change in the slope of the torque curve that can be related to the presence of the wind tunnel. Finally, we investigated the noise emissions by the use of microphones in all the conditions already examined before, but also considering some reference situation of the empty wind tunnel and the still rotor, so to have a reference to which compare the acoustic emissions investigated. So we carried out a large, extensive experimental campaign, considering, for instance, the different position of each microphone, the effect of the rotational velocity, and just as an example, this is the sound pressure level in terms of average value compared to the power curve for a fixed wind speed. Well, in this case, similarly to what we obtained regarding the wind velocity recorded downstream of the Savonius rotor, the pressure levels seems to decrease on increasing the produced power, and also in this case, these maximum and minimum values are not perfectly aligned, but then on decreasing the produced power, the sound pressure seems to increase. I have to say that this presentation was originally meant to be delivered by Professor Christoph Döffer, who was the PI and the driving force behind this project. Unfortunately, after a terrible accident, Christoph passed away in a manner that left us in a deep shock situations. And you can imagine that it was very difficult for me, but also for all of us involved in the project to carry out and to find the strength to carry out this work. I want to conclude this presentation by remembering by Christophe in this conference, and I also want to express my closeness to his family, to his team, and also in particular to his father, Professor Piotr Döffer, that found the courage to continuing the work that his son has started. So, thank you.
Thank you. I think we finish our time, so we postpone question and comments in the coffee break. Before leaving the room, I want to thank all the speakers and all the working group. And I ask the presenter of the next session to please upload the presentation before having coffee. So thank you all, and see you later.
She doesn't have it, the key, the port. Porto mio di piace. Ci serve anche l'etichetta di sì, vabbè. Sì.
Mi spiace. Sono bollito.
This is to upload the presentations.
Yes. Okay. That's good. Okay. Yes.
You should go to there is this room here, they do there, and then they send it here.
Okay.
This
Okay, perfect.
does not work somewhere.
Perfect.
Yeah. I guess we can have more questions. No, I can do it. Actually, that's
Welcome back, everyone. So we'll start the last session of the day. First presenter is Professor Dimitris Pitilakis.
Thank you, Mr. Chairman. All right. Hello, everyone. My name is Dimitris Pitilakis. I'm a professor of civil engineering from the Aristotle University of Thessaloniki in Greece. I'm here on behalf of this big team that you see here at the bottom. I'm going to present the efforts done in the project called Real-Scale Experimental Assessment of Pile Group Dynamic Impedance. And PI in this project is Raffaele Di Laura, who unfortunately cannot be here, so I am presenting on behalf of the team. So basically the user group consists of Italians, Greeks, and a Belgian. And the actual goal is to try to estimate actual impedance functions for pile foundations out of field scale testing. What is the motivation of such a study? First of all, the soil structure interaction is often neglected while having a prominent role in the dynamic behavior of the superstructure. The new upcoming Eurocode 8 is coming to fix this problem. And a big thing is that whatever has to do with SSI partially lacks of experimental validation. And with reference to real structure foundation systems or current methods and formulas. So basically, the main objective was to derive experimentally measured impedance functions of real scale pile group foundations and single piles under dynamic loading and static loading. This is the host infrastructure, of course, is us. We call it EUROSIZE Test and EuroProteas. It is in the north of Greece, just outside of Thessaloniki. It is outside in the field, so it's, as we like to call it, it's like a natural laboratory. This has a lot of problems in terms of testing, because, for example, we are always vulnerable and prone to the weather. We cannot test during the winter because it's snowy. We cannot test during July, so this creates different problems. So basically, this is, to the right, you can see the prototype structure of EuroProteas. The dimensions are 3 by 3 and 5 meters in height. It is a quite stiff structure which rests on a very soft soil profile with a VS around 100 meters per second, just to give you an idea. So basically this increases and promotes soil structure interaction effects. At the bottom you can see the eccentric mass shaker that we used in order to run such tests. The thing with our infrastructure at the EUROSIZE Test is that since the early 90s we have been continuously studying the soil conditions. So we like to say that we know very well what are the actual soil conditions. And this is the added value of doing tests over there. It is outside in the field with actual soil conditions. This is the soil profile, more or less. And now the test consists of building a pile group of 2 by 2. You can see them here. These are the 2 piles below the foundation. And there are also 3 single piles, 1, 2, 3, that are used for static testing. So basically we have 2 kinds of testing. One, dynamic testing of the actual structure. This is the foundation or the roof, and this is the position of the 4 piles. And we also have static testing. We monitor during the test the response of the structure, so the roof up there. We monitor the response of the foundation. We monitor the response at the soil. You can see here the deployment of our instrumentation in the soil. And also we have instruments placed inside the piles. These are instruments, accelerometers, placed inside the piles to record the vibration of the piles. This is the mass shaker. You can see it here. It is an eccentric mass shaker. And it has let's say, even though it is quite simple in its function, it has a basic problem that in order to produce, let's say, the force in a very specific direction, you have to orientate the masses. And this is not, it is not trivial, because you have to orientate two sets of masses that spin with several hundreds RPM, and it is very difficult. If you do not orientate the masses accurately, it means that probably you are going to create some kind of torsional response in the structure that numerical analysis and people that are doing numerical analysis are not expecting this. So these are actual conditions, actual loading, and we're trying to, let's say, interpret the results based on this. The forces that we can exert on the structure, they range from they are within the frequency of 0 to 10 hertz, and we can go up to 45 kilonewtons. So it's quite a big force. Now, first we tested just the foundation. This is the foundation slab, the pile cap foundation, which is fixed on the 4 piles. We placed the eccentric mass shaker at the foundation slab. And you can see here in these tables, this mass configuration means that for the same, let's say, there is an equation that gives the force based on the eccentricity of the mass shaker, and these are the different masses. So typically, if we use 4 masses, we have more rotating masses, and we create higher forces. This is the frequency range. So in the first experiment, we tested 18 frequencies. In the second experiment, 15 frequencies, etc. Then we had to move the structure. So we are moving Europroteas. We place it on top. We place the roof slab, and we do again some testing with the eccentric mass shaker at the bottom. But here now the structure is on top, Europroteas is on top. And then we put the eccentric mass shaker on top of the roof, and we do the full testing sequence. Now, this is the user group actually, and us, of course, we are not very advanced in, let's say, the interpretation of the data. So because we, essentially the user group lacked, let's say, people to do the interpretation of the results, this is why several months after we have not reached to the level, let's say, of the interpretation that we would like. So now here I will just present some basic results. This is basic recordings. You can see here that this is the recording of, let's say, using 4 masses and without the structure on top. We can see that it is something like a sine sweep. You can see the recorded response at different locations of the foundation here. And here, this clearly the Fourier spectrum shows the frequencies that we want to. Then we put the structure on top. The response, of course, is very different. Here we can see that we have, at this range of frequencies, we have the resonance of the system, which is something like 5.5 to 6 hertz. Here, just to mention that the fixed base frequency of Europroteas is around 9 hertz. So if we place it on a surface foundation, on the soil, no piles, no nothing, from 9 hertz, it drops down to 3 hertz because of soil structure interaction, just by that. Because the pile foundation is stiffer, from 9 hertz of the fixed base frequency, accounting for soil foundation pile interaction, it drops down to 6. So, okay, it's not as big as the surface foundation, but still we can see SSI. So here we can see, if we place the shaker at the foundation, we can see that clearly we have a resonance around 5 or 6 hertz. And this is more important if we place it on top, because if we place it on top, we create a higher rocking force, so we excite, let's say, the structural response, the foundation, and the pile response more. Now, how did we calculate the impedance functions? I remind you that the primary goal of this testing sequence was to test in actual field conditions the analytical impedance functions that exist. So basically, this is what we did. It is a group of 2x2 piles. They are interacting with each other. So there is a bit of equations involved. If we write down the equations, including inertial and kinematic interaction for this pile group, And we tested with, let's say, traditional or analytical equations that people use. We can see that our equations, let's say, produce this blue line here, and with the red and green curves and triangles or black triangles is the analytical formulation. We can capture quite well the response that Dobry and Gazetas in 1988 had proposed. So we found that for this specific case, these equations produce a quite well response. There is a slight problem here at the damping. So to the left is the stiffness, to the right is the damping, but damping is always more difficult to calculate. And now how do we calculate the actual impedance functions from our testing? We use this simplified model for which we write down the equations of the motion. Then we have the response, and because it is something, our structure is something like a single degree of freedom structure, we can decouple the equations. So we can decouple or analyze, let's say, the response in the three principal components, so the foundation translation, the foundation rocking, and the structural flexure. If we do that, we can have the response of each one, let's say, of these contributing factors for a specific frequency. This is why the amplitude here is stable. It is the transient response for, let's say, a frequency that we want. With double integration, we go to displacements because we record acceleration. Then we have the exciting force. This is the exciting force that we get from the eccentric mass shaker. It is an analytical equation. We do everything in the frequency domain, and we get the response. By getting the response, we can calculate the horizontal and the rocking stiffness components that comprise two, let's say, distinct behaviors. The first one, the real part, is the stiffness, and the imaginary part is the damping. So basically, I'm going to show you some results from this specific test. And this is what we get. So to the left, we can see the translational dynamic impedance function. Always to the left is the stiffness, and to the right is the damping. For the same test, to the right over here, you can see the rocking dynamic impedance. The red line is the analytical equation, and the blue dots are the empty bullets here, are the results that we obtain for different frequencies. One would say, well, there are different comments that one can make, but one can say that the stiffness more or less is okay. So we are able to capture the stiffness properly. Here and here, the translational stiffness and the rocking stiffness. Obviously, there is a problem in damping. So the lateral oscillation damping, let's say, and the rocking oscillation damping, there is a problem, especially for the lateral case. This is very difficult, actually, because I didn't to capture the damping, because of the nature that we are running the tests. The problem is that our force and our response do not have the common time. Because we are outside in the field, we are not able to plug all instruments that produce the force and record the response in the same data acquisition system, which means that we get, there is a certain time lag that we cannot actually capture. The second problem is that our eccentric mass shaker does not connect to a GPS, because someone might say, why don't you connect everything to the GPS? The eccentric mass shaker does not connect to the GPS. So this is all from back calculation, and my estimate is that probably there is something like that involved in the estimation of the damping, and obviously we need to keep on working on this. So just to conclude, these are preliminary results, as I said. There is a quite good matching between experimental and analytical impedance function. It is more or less in the same order of magnitude, which is already, it's nice. It's good because it is real case, field testing. The stiffness matching is better than the damping. probably because there is no common time in force response and we cannot capture this lag in the response. And obviously, we need to process data recordings within the piles, and I believe that this will increase the, let's say, the validity of our response. Thank you very much. On behalf of the whole team, obviously.
Thank you, Professor Pitilakis. Before continuing, we have time for any questions because we are missing one presenter. So please go ahead.
Dimitri, do you instrument the soil profile along the depth or just on the surface?
You mean on the piles?
Around the piles, the soil profile?
No, just the surface. Yeah. The problem is that even if we create big forces on the structure, our instruments are not that sensitive to record something within the soil at a distance. A few years ago, we showed that when we excite the structure, even if we excite it with high forces, like 20, 30 kilonewton, we do not record anything outside of a radius of a diameter of 2 to 3 times the foundation width. We see nothing with high accuracy instruments, high resolution instruments, so we see nothing. And this is why it is even more difficult to record something like that within the soil. Any question?
When you use the mic, speak to the center, okay?
Yeah.
We are recording, and the people that want to make a question have to speak to the microphone, okay?
Okay.
Sure, thank you. So my question is about the soil nonlinearity. So the idea of dynamic impedance function is based on linear elastic soil domain behavior. Is your dynamic impedance function different if you apply different force capacity at the same, apply the force at the same frequency?
I'm sorry, but I didn't understand.
Okay, for example, let us assume that you're imposing same frequency of force and measure displacement. And now, in the next step, if you increase the force at maintaining same frequency,
yes,
you still get the same dynamic impedance function?
No. We get a different.
So then you will have multiple different dynamic impedance functions as a function of...
The function is itself is the same, obviously. We're using this let's say this procedure, the very same procedure to back calculate the impedance functions from the acceleration recordings for all the frequencies.
Yes, but if the soil behaves in the inelastic range, then this force deformation relationship will be different.
True.
So then, is there application limit of your dynamic impedance function considering inelastic behavior of soil?
No, we cannot do this. We have to assume elastic behavior of the soil.
Okay, thank you.
Otherwise, it's very sparse, the impedance functions for non-linear soil behavior or equivalent linear soil behavior. Of course, they are different.
Right, if there's no other question, we will move on to the next speaker. Thank you. So our next speaker is Dr. Maddalena Ponte, who is going to talk about masonry, I believe.
Hello, everyone. I'm Maddalena Ponte, and I'm going to present our ERIES project. Is named Restoring, so retrofitting of stone masonry using innovative grid-based composites. We are focused on the vulnerability of stone masonry buildings, and these buildings are usually vulnerable, firstly to the out-of-plane damage mechanism due to the overturning of the walls, but also to the in-plane damage mechanism governed by shear or flexural failure. And in this case, we want to reduce the in-plane vulnerability of these buildings. By that, we are studying the application of retrofit systems, the CRM strengthening, composite reinforced mortar, which is composed of a glassed FRP mesh, in our case, with electroidal connectors, and a structural hydraulic lime cement mortar. The other strengthening technique that we studied is the FRM, fiber reinforced mortar, which is a technique faster to apply on site because it does not require the use of the mesh. It's a fiber reinforced cementitious mortar of high performance. And our ERIES restoring project is a user group coordinating by the technical team here in Lisbon, also composed of the University of Pavia and the UPC University in Barcelona. The facilities where the tests were carried out are EU Center in Pavia, and we had an industry partner, Rura Gold from Laterlit, that provided us the materials. Our test specimens were full-scale specimens with two geometries, a slender geometry and a squat geometry, and different retrofit combinations were considered. So two specimens with bare masonry, one for each type of geometry, were considered as reference. And then CRM applied to one side and CRM applied to two sides were also studied for each geometry configuration. And then also FRM applied to two sides only for the slender pier configuration. The masonry used was a double-leaf natural stone masonry with rockly dressed blocks with approximately 30 centimeters thick. The stone was calcareous and the mortar was hydraulic lime mortar. The masonry was built in order to represent the historical structures in the Mediterranean countries. You can see here the construction of the full-scale specimens, but also of the characterization specimens. So characterization tests were carried out to characterize the bare masonry under vertical compression test loading and diagonal compression loading, but also with the CRM on one side and on two sides. And you can see here in the graphic that the main mechanical parameters that we could obtain from these tests. So there was a high increase in the tensile strength because we had, when applied the CRM strengthening, we had a very low, very weak masonry, and so therefore the tensile strength increased a lot, and then the compressive strength increased just a bit less, just due to the confinement of the connectors. This is the test setup. So our main tests were the quasi-static cyclic shear compression tests. This is a test setup for the two specimens. Double bending configuration was imposed with the constant vertical loading. That was 20% of the masonry compressive strength. The double loading was imposed by restraining the top rotations of the piers through the two vertical actuators, but always keeping the sum of the vertical force is constant. And then the horizontal cyclic loading was applied until 20% of lateral strength drop, or when the specimen lost the vertical stability. These two configurations were considered, the geometry configurations were considered to study the flexural behavior, flexural failure with the slender piers, and then for the squat piers we intended to study the shear failure. The instrumentation applied was made of traditional instrumentation, made of 40 sensors applied mainly on the back facade of the specimens, and then on the front facade of the specimens that we could see during the test. It was the digital image correlation through this scattered pattern of black dots. Here are the results with the DIC, the digital image correlation for the slender specimens with the bare mason configuration and the CRM on 2 sides. And the good thing from this technique is that we can identify the onset of cracking that we cannot see to the naked eye during this testing. And you can see here that the not retrofitted specimen had a hybrid flexural type of failure with also diagonal cracking, but still being able to transport the load diagonally, so the edges were not extruded from the specimen. And then with the CRM on 2 sides, we have the flexural behavior, the rocking behavior with the crack on top and bottom. And here also the behavior of the squat specimens, bare masonry and the CRM on both sides. We're still working on this data. They are not at the same velocity. In fact, the cracking on the bare masonry appears much before than on the CRM. But you can see that they have the shear type of failure. And we can also see that by applying the CRM, we have a much diffusion of the cracking of the diagonal cracks. And then we can compare the cracking pattern from the DIC with the one that we visualized on the back facade of the specimen. And we can notice that with the bare masonry we have a lot of similarities with the cracking, the damage pattern in the front and the back facade. And then with the CRM on one side, we can see that the front facade, that was actually the retrofitted facade, presented less damage than on the back facade. Here are the hysteretic curves obtained from the test for the slender specimens. We see an increase of strength, an increase of also deformation capacity. And again, you can see that the retrofitted specimens, either with CRM or FRM, presented a flexural shear failure, flexural failure, sorry. And then with the squat specimens, we have also increase of strength, increase of deformation capacity. Here we have a shear failure. And for the specimens with the CRM, we had at the end of the test also the detachment of the retrofit layer. The backbones of the curves are also presented. They are very important because then they will give us the main factors that we will use and need for the design of this retrofit for the design of the retrofit techniques. So with the CRM on 2 sides, there was a strength increase by a factor of 1.5, a displacement capacity at 20% strength loss increased by a factor of 3. And with CRM on one side, the increase was lower, increase of strength by 1.2, and displacement capacity increased by a factor of 1.4. Comparing the CRM on 2 sides with the FRM on 2 sides, we can see that the increased factors in strength and deformation capacity are very similar, almost the same, but we can see that FRM lead to a stiffer behavior and also a different behavior post-peak due to the faster propagation of the cracking, since there is no mesh here in this retrofit. And for the squat specimens, failing due to shear, we have the CRM on 2 sides with an increase of strength by a factor of 2, and ultimate displacement capacity increasing by a factor 1.5. And CRM on one side with strength increase of 1.4, sorry, and ultimate displacement capacity increasing by 1.2. Just here, main conclusions, because this was a very big and large project, and we have a lot of conclusions, but just very resumed, just to show you how with the retrofit we can have a more diffused cracking, as you can see here, comparing the bare masonry and the retrofit on 2 sides. And then just to leave you with the main results that in the end the practitioners will need for the retrofit, for the design of the retrofit on this type of material, since there are not reference values for this, and this is very important. So the enhanced factors of ultimate drift enhancement and lateral strength. Also, we also carried out predictions or analytical predictions of the strength of our specimens. We adapted from the FRP regulations, and you can see that also they correspond quite well to what we had. So this is also useful for the future design of these techniques, to know that they can be also, the strength can be quite well predicted. And just for future developments, defining design formulations, and also calibrate numerical models with the CRM retrofitting on rubble stone masonry. We have started already developing some with the finite element modeling for the characterization tests, and also for the quasi-static cyclic test, shear compression test. We are still developing with new macro elements. And just thank you in name of all of the team. Not everyone is included in this photo, unfortunately, but almost everyone from this team is presented here in the Congress, so if you want to talk with us, we are here.
So we have time for questions. If anyone has one, please go ahead. I guess there's no questions, so we will continue. Our next speaker is not present at the moment, and we will continue with Professor Francesco Graziotti.
Good afternoon, everyone. Let me search for my presentation. Is this one? Yes. Good afternoon, everyone. So the project name is Out of Plane Shake Table Test of Reinforced Masonry Gables, considering different roof configuration. The actual name is Supreme, ERIES Supreme. Don't ask me how it's possible from this title goes to Supreme, but this was somehow possible. The partners were University of Pavia, so my university, TNO, that is a consulting company, research consulting company in the Netherlands, and TU Delft. We conducted the test in U Center, Pavia. So it is very clear that gable walls are very vulnerable. This is due generally to the high slenderness of this type of walls, low vertical overburden, seismic amplification that we may have that we had at the highest level of a masonry building, and generally a weak connection to the roof structure. Despite this, there is a very, very limited experimental observation. One of the unique, the only shake table test on gable was conducted, specific on gable was conducted here in Lenec, in LNEC, in 2012, I guess, in collaboration with Antonio Correa. This is here. In that case, we built the entire roof structure in order to test the cable. It is very, very clear that there is a filtering effect of the structure. This is a very old picture from 1985 by Nigel Priestley, where this amplification effect and the fact that we may have different acceleration, that we have different acceleration on different floors is very, it is and was very clear. Especially for roof structure, you have also to consider that on top of it, you may also have a very high differential displacement in the two levels, not only the acceleration. So the idea of this Supreme, now you see how it is possible to go from seismic out of plane response of masonry gable to Supreme. Dr. Sharma from TU Delft actually had this fantastic idea. The main goal of the test was to test these gables controlling actually the two differential motion in terms of displacement and acceleration. So the setup allowed to control the two differential motion, to have a known boundary condition in order to give the possibility to easily numerically replicate the test, for example, also maintaining a constant overburden load, in order to be numerically reproducible. Let's say that the funny part of the project was to create and to mount the setup. We use the 9D lab in 9D facility of U Center. This facility actually consists of two shake tables, one on top of the other. The bottom one is a 6 degrees of freedom shake table. On top of it, with 4 braces, trusses, guaranteeing the vertical compatibility of displacement, another shake table is placed with other 3 degrees of freedom motion, so 3 degrees of freedom, so 2 horizontal and 1 rotational around the vertical axis. This setup, or in general this facility, allowed to control and uncouple the acceleration and displacement of the two floors. For example, it may simulate what is happening at the 10th floor of a building, considering also the acceleration at the 11th one, considering also the drift between the two floors. We use it in order to actually apply what is happening at the 2nd floor of a masonry building, considering the motion of the roof that could be rigid or not. We conducted 3 different tests on 3 nominally identical specimens. One with a, let's call it, stiff roof, so basically with nominally the same acceleration top and bottom. Another one with a semi-flexible roof, so with a difference in acceleration top and bottom, but with the same accelerogram, so something that was completely in phase and with the same accelerogram scaled up. And then a completely flexible roof, where we actually simulate a roof that was actually responding in a completely different way compared to the bottom structure, also with some out of phase accelerations. The tested specimen had this dimension. Actually, the table, the 9D shake table, had a dimension of 4.8 times 4.8 meter, but we actually exceed the limit of the table, and we had the chance to build this 6 meter long gable, 6 by 3 in height, and the idea was to test these gables without anchors. So we wanted to, being this the first test around, we wanted to test the most vulnerable possible configuration, and we decided to rely only on friction between the timber and the masonry. This is a very vulnerable situation, but that it is absolutely present in the building stock. We heavily instrumented the specimen, as usual, with accelerometers, potentiometers, traditional potentiometer and wire potentiometers. We maintained the vertical overburden load quasi-constant through these springs that allow actually the small movement of the specimen without changing too much the vertical compression, and we monitor also this spring elongation. We also used these optical markers. So these are 3D acquisition system that is used also. We can use also in dynamic in order to have the position of these points that are like table tennis balls, just to to give you an idea, have a 3D time history position of these balls, and in order to recreate, for example, the deformed shape, or in general control all these points. The input selection. So basically, this test was conducted in order to study in general the gable behavior, but in particular with reference of the Netherlands. You probably know that there is a issue with induced seismicity. And the idea was to further validate the models that are around, and also the code, the prescriptions on these elements. The induced seismicity, the earthquakes are very, very, very low, so we also take chance to study further with a higher intensity. So, considering the induced seismicity, we use a numerical model, finite element, very detailed finite element model of a terrace house, in order to have basically the floor motion, as well as the ridge beam accelerogram of the three configurations, so rigid, semi-flexible, and flexible. And we actually succeed in having the accelerogram to be assigned to the two tables, with a pretty decent smooth spectra, because you have to also consider that in this type of test always is much better to have something that is relatively smooth in terms of spectral acceleration, in order to study in a more robust way the actual behavior. Also, if you want to reproduce it numerically. For the tectonic seismicity, we decided to do another thing. We had access to this structure in central Italy, in Visso, that was hidden by the sequence of 2016, as you see, with a pretty heavily partial collapse of the structure. This was a school. And we had the floor motion of this structure. So we use directly the floor motion of this structure, and we adapt this floor motion to simulate. In case of stiff roof, we simply use the floor motion 2 times. In case of semi-flexible roof, we scale up the exact floor motion, and in order to consider a complete flexible roof, we used a 0.5 second single degree of freedom elastic, 5% of damping, in order to have the 3 spectrum. Actually, this process was so tricky that we recently was accepted on Structure a paper specifically on how we actually compute these motions. Don't look at all these numbers, but just to show that we also succeed in having something that was compatible. So the two completely different motion. As you may expect, we conducted an incremental dynamic test. There was this kind of continuity between the first floor motion and the second floor motion, so the induced seismicity and the tectonic floor motion, with increasing different intensity measures. This is a video of the first test, so the one that had nominally exactly the same acceleration top and bottom. You may see there is kind of some small, let's say, out of phase of the 2 tables, but this is nominally the one with the same acceleration top and bottom. As you see, you can read on top of the video. We reached a pretty high acceleration of almost 2g at the base. The second test that we conducted, we had the privilege to conduct the test live during the last day of the World Conference in Earthquake Engineering in Milan in July, was the one where we had actually the semi-flexible configuration. So the accelerogram, top and bottom, was the same, but the top one was actually increased in order to have a higher acceleration. As you see, in this case, the base acceleration at collapse was lower than before, as expected. The third one was the one that we were more curious about, was the one with a complete different acceleration, top and bottom. You really see how the top shake table is really accelerating a lot. In this case, we reached a 2.5 G on the top one. And as expected, also in this case, the base acceleration at collapse was lower than before. It is relatively difficult to interpret the data and also to write down what's happening on a paper, because all the also the collapse shapes of these specimens were different and were actually a function of these different acceleration on throughout the height of the specimen. Let's consider two measures. One may consider, in order to calibrate a numerical model, the deflection of the gable as a beam, so the deflection from the rigid motion. Another possible interpretation could be summing this deflection to the rigid motion of, for example, of the centroid. Why it's important? Because this is the we call incremental dynamic responses. It's like an IDA, but IDA, but a test IDA. So we're increasing the peak base acceleration, and we measure the, for example, in this case, the deflection of the gable. You may see that, as expected, going from a stiff, so with the same acceleration top and bottom, towards a flexible, so with a higher acceleration at the top, and adding also a very high displacement, the differential displacement of the two tables, we had a pretty dramatic decrease in the capacity, in acceleration capacity at the floor. Consider that today a lot of engineers are using these as input parameters, so the floor acceleration. Okay, things are going kind of better if we consider, at least for the two gables that were subjected to an in-phase motion, if we consider as an input not only the bottom acceleration, but a sort of average spectral acceleration doing the mean of the top and bottom table. You may see that, for example, the two curves are very similar. And again, this could be even better if instead of the gable deflection, we also somehow including in this gable deflection a sort of interstory drift. But this is just very preliminary results to reaching the point that it is now very important to interpret this data, model these structures, try to maybe conduct parametric study in order to really understand how it's possible to treat all these input parameters, so not only the acceleration but also the drift, in a possible assessment of this type of structure. And again, I'm not only referring to the gables, so triangular thing, but also to a simple one-way bending beam, one-way bending wall responding out of plane. It would be very, very important to understand how this wall is responding to the very different response top and bottom. We also had the chance, interpreting also the accelerometric data that we have, to plot hysteretic response of the gables. We succeed in this. This will be very, very useful in order to calibrate numerical models. We also launched, before the test, a blind prediction competition with a special issue on Bulletin of Earthquake Engineering that will publish in the next month. And actually, we were surprised that 8 plus 1, but let's say 8 researchers, 8 groups actually sent their contribution. And we also very happy that the top ones, so the 2 or 3 that performed better, actually did a very, very good interpretation, blind prediction of the test. Both the rigid one as well as the flexible one. So results of this will be published in the next month. So now what we want to do with this data, and what we actually hope that other researchers are doing with this data that will be freely available as all the data of the project. For sure, developing some numerical modeling, maybe using DEM or finite element model, in order to have to simulate further tests, maybe changing parameters, boundary conditions, input. You can imagine what we can do with the model together. Also create some numerical benchmark to calibrate simplified numerical models in order to really conduct a lot of parametric study on these. And these should absolutely take into account the differential motion, not only in terms of acceleration, but also in terms of displacement of the 2 levels. With this parametric analysis, the idea is to update or revise or write something about the code prescription and how engineer can handle this and assess this type of walls and structural components. Again, there will be a special issue on the bulletin in the next future, not only on the blind prediction, but also in general on the seismic out-of-plane response of these unenforced masonry gables. Thank you very much for your attention, and I have to thank all the youth center staff and also all the students and collaborators for the very nice period that we had during this project and conducted this work. Thank you very much.
Thank you, Francesco. Indeed, very interesting research. We have time for one more question, if anyone wants to ask.
Thanks for the supreme presentation. And one of my questions is related to the boundary conditions that you have used.
Yes.
Because you have only transverse beams,
yes,
which is not really clear to me, at least, how long they are. But more importantly, why you have neglected a sort of a belt that is generally used in construction.
Okay, for different reasons. One is to make it simple. So we wanted something really, since this one is the very first one, something that was really reproducible with a numerical model. It is representing, in my opinion, the limit case. This could be a possible solution in some very, very peculiar cases, but the real idea is to make it simple. Because it's not, also in this case. And then concerning the beams, basically you can see maybe from this picture. Now it is collapsed. The thickness of the specimen was 10 centimeters. Again, first of all, because this is a typical dimension of the Dutch gables, but also because in reality we needed something to study. I mean, we were not really focused on a specific type. With a thicker thicker gable, maybe we needed to go to higher acceleration, even higher acceleration that is complicating the life every time. And concerning the length of the beam, okay, there was a full contact between the beam and the specimen, so 10 centimeter contact. And I guess that this was the question, right?
Yes.
Okay.
Last
Yeah,
comment. Since
please.
you're doing further work, I mean, to which extent induced seismicity can be comparable to wind? Since we are also talking here about multiple hazard.
It depends. I mean, I'm not a wind expert. I guess it's depending on the wind. What we observe is that first of all, there is a huge difference, in my opinion, from induced seismicity recorded and possible hazard of induced seismicity. Now, with the time and with more study, also the knowledge that the seismologists are gaining on the induced seismicity is actually letting this hazard decreasing a lot. When this project, the project on induced seismicity that actually involved the center 10 years ago, the hazard was relatively high, was compared to the tectonic earthquake. So in that case, okay, wind is maybe nothing. Now I guess that if I have to think about the real earthquake that they have in the Netherlands and the real wind that they have in the Netherlands, maybe wind is governing. But I'm not absolutely not a wind expert, so I cannot answer you.
Thank you.
Okay, thank you, Francesco. We'll move on to the next presentation. Professor Ivan Jongo.
Thank you for the introduction and good afternoon to everyone. I think I'm the last, right? So it's a hard job to keep everyone awake before dinner. So I'm about to talk to you of the ERIES Strong project. ERIES Strong stands for Sustainable Timber Retrofit of Concrete Buildings. And here you can see the partners. There's the University of Trento, where I'm from, University of Patras, which is where we did the testing in the Stru Lab, University of Pavia, and also there are two industrial partners, Ixlan Dolomiti, which is a company in Italy producing CLT, and Python Fixing, and the name says what they do, and they're from New Zealand. As we all know, reinforced concrete buildings constitute probably a very large portion of the existing building stock all around Europe, and that's true also for the earthquake-prone countries. And many of these buildings predate the modern seismic codes, and they've been designed exclusively for gravity loads, which means that they've proved and it's been proven that they're highly vulnerable to earthquake, as you can see from common picture that most of you have surely already seen. And there's an aspect that oftentimes is neglected when assessing the performance of this type of buildings, which is the role of the infills, and that many times and time again has proven to be central, as they have a very strong influence of the overall response in terms of strength, stiffness. They influence the period and thence the demand of the building. They also modify the failure mode, and they transfer additional shear to the column, which might prove fatal in some cases. And so the goal of the ERIES Strong is to provide full-scale experimental evidence on the effectiveness on a timber-based seismic retrofit strategy that is named RCTP. We're not very original in names, not as supreme, I think. And in its original form, it's as you see here. So the idea is so the first thing is to remove the strong infills that can be potentially dangerous to the columns, and thus reducing the seismic mass. Then there's a timber subframe which is installed and fixed to the existing concrete frame. The subframe is supposed to remain elastic, and therefore the connection can be obtained as, for example, as you see here, using steel rods bonded with resin. And then there's the insertion of timber panel, and in this case they are CLT panels. And as you can see, there's a gap surrounding the panel, which has two main reasons. The first one is that without any gap, you cannot insert the panel, so that's very simple. And the other one is to avoid any direct contact between the timber panel and the frame, so to avoid any strut mechanism. And so we can engage the dissipative abilities of the timber-to-timber connection. So the panel is fixed to the timber sub-panel using timber screws. Common from the shelf single-thread timber screws, which are very good, they're ductile, they're very good response. So previous stages of the research focused on frames representative of the 70s, as you can see here. And they proved that this technique can improve significantly the lateral capacity of this kind of structures, and also improve the deformation capacity, and at the same time favor more ductile response, so less brittle failures. With ERIES Strongs, there are some important novelties. And well, the first thing is that the system has been updated, and the first difference is that now it's fully dry. So also the subframe is installed, as I said, dry by using this 340 millimeters long screws originally developed for masonry. They have a double thread, a front thread that is for masonry concrete, and then a rear thread that is for timber. And also, we are now focusing on frames representative of the 50s and 60s, with the typical cavity infill walls, which comprises a strong leaf made of solid bricks and, let's say, weak leaf made of hollow blocks. And so the idea here is to remove, just to improve the invasiveness of this type of retrofit and reduce disturbance to the occupants. The idea is to remove just the strong and potentially detrimental infill and leave the weaker infill made of hollow blocks. And of course, once we decide to keep this, then the out-of-plane failure must be prevented, or make sure that it doesn't happen. And so it has to be secured by using special screws that you see here. It has to also have double thread, but they are the same thread with a smooth part in the middle, that they secure the blocks to the CLT panel. Also, we decided to get as close as possible to a more realistic scenario, and so we have two stories, a multi-story, multi-bay frame with the geometrical features of the base, which are different, so different aspect ratios, and also there's the presence of openings that wasn't tested before. And last but not least, we also wanted to apply some non-structural layers. In particular, here we have ventilated cladding in order to see its compatibility with the deformation of the retrofitted structure once it reaches the ultimate limit state conditions. Today, I want to focus more on the design phase of the testing campaign and share with you some feedback on the, I'd say, typical yet inevitable challenges that we all have to face when ideal meets real. And so, well, here you see the specimen, the geometry of the specimen. As I said, it's a two-story, two bays. And it's intended to be representative of frames from the 50s and 60s, which are 2 decades which are quite relevant, especially for Italy, because in that period we experienced an increase in the number of reinforced concrete masonry filled frames that is 12-fold, from 70,000 more or less to almost 1 million buildings, which are typically characterized by this scenario of having strong beams and weak columns because of the detailing mainly focused, well, I'd say exclusively on vertical gravity loads. We did the design of the specimen according to the standards that were in force at the time, and here you see an excerpt of the Royal Decree from 1939, and also keeping in mind what was done in the real world, so the practice, and the analysis of the original design documentation showed something that I think everyone knows, that sometimes the rules were not actually followed by the book, and that was due because of sourcing of the material, cost-cutting measures, and lack of rigorous inspections. So for those decades were mostly used plain or smooth bars, and by doing research on the state of the art, the most probable material properties were selected, which for steel was this yield strength of approximately 320 MPAs, while for concrete, compressive strength that is around 14 MPAs. And here the first bump, of course, the representative value that we ideally desired for our bars was 320 MPAs, but the plain available bars were 220, and so in order to, which is still okay because it's on the lower bound of what was actually available at the time, but in order to ensure the same hierarchy of collapse mechanism that we would have by taking into account the most probable properties, we had to modify and have a reduced target compressive strength for the concrete, and we did that by looking at the ratio between the different mechanisms and keeping that constant. So in the end, we still ended up with what we wanted, so a scenario that is a strong beam, weak column, so the column are the most vulnerable, but the beams have some extra strength that we can tap into with our retrofit system, which is kind of trying to have to force a direct transfer from beam to beam and release a little bit the columns. So previous research that we did, some parametric studies, revealed something that is expected, actually, so that if we apply the fastener, so we connect our CLT panels on the beams and also on the columns, then applying the fastener on the columns increase the overall lateral capacity. As you can see here, these curves, the higher up is the one with the closest fasteners on the columns, but in turn, of course, you have an increased shear demand of the column, which might be counterproductive if the columns are the most vulnerable. So we decided to go for this scheme where fasteners are applied only on the beam sides. And the goal is to balance, to find the right trade-off between increasing the lateral capacity, so to have a stronger, stiffer connection, but at the same time, we don't want to engage brittle failures. We want to delay brittle failures as long as possible. So in order to do that, we did some modeling. We tried to simplify. We had some very refined modeling we did in Abacus and so forth, but we went for simplified models that you see here, where well, the frame is modeled with frame elements, concentrated plasticity. The infills are modeled as equivalent strats by adopting the model proposed by Liberatore and others, and with the material properties that were calibrated on previous small tests, material characterization that we did in our laboratory. And here you see the model for the retrofit part, where the CLT panel is modeled using shell elements. And then we have a series of nonlinear link elements that can simulate the connection. So the subframe to frame connection was assumed to be rigid because we want it to be over-strong and also stiffer than the timber-to-timber connection that is the one supposed to ensure dissipation properties and ductility to the whole strategy. So, well, then once we select the connection, and the connection that was actually the timber-to-timber connection was made with, as I said, run-of-the-mill single-threaded screws. In this case, it's 10 millimeters because that's the optimal one in order to have the double plastic hinges form into the fasteners. And then so the design comes down just to spacing because of the fasteners, and you see here some of the results from the parametric study that we performed by changing the spacing of the fasteners on the panel to subframe connection. And as you can see here, the optimal one is this one, which is not the one that provided the highest lateral capacity, but is the one where we can go further without incurring into brittle failure, like the beam shear failure. And so the final design choice was this one, with 15 centimeters at the ground floor and 20 centimeters at the top floor. So this is the actual final details for the retrofit of the specimen, as you can see here. But based on the data available at the time for the subframe to concrete frame connection, the one done with the 340 millimeters, let's say, masonry screws, well, the data provided by the producer was not as great, so we had to prescribe this insertion at an angle to the grain, an angle to the surface, in order to engage the pull-out strength and the actual response, which is stiffer. And of course, this is kind of a nightmare from the application point of view. No one is happy for that. So the idea was, let's see if we can improve from here. So then some typical material characterization tests were performed. And as always, not always as was expected in advance, otherwise would have been pointless to do those tests. And for example, the available material for the infills proved to be much stronger than anticipated, and the infills resulted to be really with a higher strength and stiffness than anticipated. And so you see here the changes from the dashed lines to the continuous line from before the specific data and after this testing. So that meant that we had to update the retrofit in order to see meaningful results, and of course reduce the spacing and then calibrate everything again. But then one might wonder, okay, if you reduce that, you could incur into brittle failure that you didn't want. But luckily enough, also the stirrups proved to be stronger, so the yield strength was higher, closer to our original desire, and then so that meant that in the end the balance and the hierarchy in terms of collapse mechanism was okay. And also the timber concrete connection proved to be better, but that was kind of a hope that we had. And so we had a higher strength when working shear, 20 kilonewton each. That's the lateral capacity, and the pull out is 50 kilonewton. So that is strong enough so that we could prescribe a different application. So 90 degrees, so easier to apply, something that is doable actually on site. But then it means that when moving them from actually loaded to laterally loaded only, we had to take into account the deformability, which wasn't included before, so we had to update the model. And of course, we updated the curves that I'm not showing you yet. Here you see some of the pictures during the construction of the specimen. These are the two bare frame ready before the construction of the infills. This is the specimen representative of the as-built condition. And then here you see some details on how the vertical load on the column was applied. It was approximately 200 kilonewton per each of the column. And over here you can see the studs that were used to connect with the 4 hydraulic jacks that provided a seismic lateral loading. Here instead you see some pictures of the retrofit and the retrofitted specimen. As you can see here, there's the fixing of the subframe to the concrete frame with screw anchors. And then there was the building of the weak leaf. Of course, ideally you have that in place and then you install that, but this happened for logistical reason and also for workforce scheduling. And also it's easier to be done. That's something that we cannot hide. And then placement of the internal measuring device, so the ones that are measuring the performance of the timber to concrete connection. And as you can see here, then the application of the CLT panel with the gap, which is fundamental for the mechanism that we want to engage. Here you see the fasteners that were used to prevent the out-of-plane collapse of the hollow block leaf, so that connecting the blocks to the CLT. The CLT is a 3 layers CLT, 6 centimeters thick. And then there was the fixing of the support rails for the ventilated curtain walls, and then the finishing tiles, which are quite big, 1.2 meters by 60 centimeters. Here you see the both specimen fully instrumented and ready for being tested. And here we have the results. So we can see that in the end, despite everything, there was a 24% increase in lateral capacity, and the ultimate displacement increased as well. Then also the updated model with the input data from the material testing was able to predict the experimental response quite well, but we are still processing the data, so more info, more details, and more insight on the results will be provided at the ERIES session at Compton, so early in 2 months actually. And well, some of the conclusions, which I can summarize very quickly. So the goal was to test and prove the effectiveness of this timber-based SCTP retrofit applied to frames representative of the 50s and 60s up to ultimate conditions. And the frame were 2 stories, 2 bays, and with some aspects that were never investigated before, so the possibility of maintaining the internal width, so to reduce the invasiveness of this kind of strengthening intervention, and then the effect of the openings, and also the interaction with the finishing non-structural layers. Of course, there are some challenges. There are always challenges and that need to be faced, so sometimes you have to update kind of your goal and your targets while you're going. But the results showed appreciable improvements in both lateral resistance and displacement capacity. Thank you for your attention. I've kept the picture with all the people for the next.
Thank you, Professor Ivan. Indeed, it was a strong work. I guess we have no time for questions. So if anyone wants to ask...
I think everyone is happy to go for dinner.
If anyone wants to ask a question, please go ahead and dinner. So thank you for coming.
I will just add a few notes about tonight. So the dinner is at 8 p.m. in Espacio Tejo, if I said it correctly. So on the program, there's a QR code. It's downtown somewhere, so you'll find it that way. there was a second thing. Oh yes, tomorrow morning. We start at 9 a.m. They're not technical sessions, they're working sessions, so they may be a bit boring. But it's a step back, and I really hope that everybody will come, because it's the kind of stuff that will help future projects like this. So the idea of data management policy, stuff like that, it's not very, let's say, attractive, but it's the kind of stuff that keeps these initiatives going. So yeah, see you later, and let's hope it's not too late.